Given by Professor Bob Evans from physics in Bristol, and you can see the title there, Density Functional Theory for Hard-Body Models of Liquid Crystals.
Thank you very much, Claudio, and let me thank the organizers for inviting me. I hope this follows on sort of smoothly from what Don Frankel has been telling you about. I'm going to be talking about hard-body models, and this is my subtitle. Of course, as Don has hinted, I have to add what it says at the bottom because Mr. Onsager knew everything about everything, and so this is specific to this. Also, following on from what Don said, it's certainly a long time since I worked on liquid crystals, so I'm here by false pretenses. So here's the outline. I'm going to remind you quickly, though Don's done this for me, what Mr. Onsager did and said in those two papers. It's a second virial treatment of bulk phases. Arguably, it was the simplest possible density functional theory you could dream up, but arguably also one of the most intelligent. Then I'll go on and say what is required of a theory for treating hard-body models, and I'll be talking about both bulk, but primarily interfacial problems. I'll then give a rapid summary of the formalism of density functional theory. I know that some of the audience will be very familiar with this, and others might not be. Then I'll move on very quickly to hard spheres and the work of Rosenfeld and subsequent developments, which was mainly for spherical systems, but a few years after his first paper, he turned attention to hard convex bodies. And then there was a period of time where not much happened between the Rosenfeld 1994 paper, apart from a brilliant paper by Friederike Schmidt, who I think is in the audience, to recent work by Mecker's group. And I hope to tell you a little bit about what Klaus Mecker has been doing. And this is to do with capturing the Onsager limit. I don't think I'll have time to talk about topic 6 and 7. If anyone would like to ask me about it, please do. So there is the 1942 Onsager paper, and that's all it is. That's the total of that paper. It appeared at as an abstract for an APS meeting. And you can see what I've highlighted. He was interested in hard body systems because of the experimental work on tobacco mosaic virus. And there is a slide, a picture of tobacco mosaic virus, and I hope you can see rods of 300 nanometers in length, 18 millimeters in diameter. So in Dan's language, in my language, length over diameter is about 17. It's a large aspect ratio. I'm not showing you the 1949 paper. Don has explained to you why that's important, why it's clever. All I'm showing you is the bibliography. There are only 4 references, and those of you who come from a sort of colloid and soft matter background will recognize these as all very famous people. In the paper, of course, he does expansions in the Meyer function, and he refers in the text to Meyer and Meyer, but doesn't give them a reference. So once again, what is Onsager trying to do? He's trying to distinguish between an isotropic and a nematic phase of these hard spherocylinder-like objects. Once again, Don has outlined this for you. This was one of the first examples of looking at phase behavior in a system where you have only repulsive interactions. So the internal energy U plays no role. F is the Helmholtz. S is the entropy. So the internal energy does not matter, but that does not mean that you can't have interesting phase transitions, as we all know. So a theory would obviously like to give you the various phases. These are cartoons of the ones we've already seen from Don. So reminder of what Onsager found, and again I think Don hinted at this, for the bulk transition, this dimensionless density C, which is defined like this, rho is the number density. This is what Onsager got with his clever trial function. that's the isotropic value, that's the value in the coexisting nematic phase, and these are the numerical results. So Onsager does well. I can't remember the values for the order parameters, but they're within a few percent. I certainly remember that. And here's a cartoon showing you what excluded volume means in this context. And here is the famous expression for the bulk free energy per particle. So this involves an ideal gas term, an entropic term. This involves a mixing entropy term, orientational entropy. F is the orientational distribution function. I think Dan also called that F of omega, maybe little omega for Dan. And this is the excluded volume term, and this it works up to second virial level. So it involves an integral over orientation of the product of these two orientational distribution functions, and gamma is the angle between the rods. But this talk will focus a lot on inhomogeneous systems. So I'm thinking of problems of interfaces, interfacial phase transitions. And so in this case, the average one-body density depends on orientation, omega, and on the position of the particles in the system. And so let me remind you of just a couple of examples of this, the sort of physical problem I might be interested in developing a theory for. So the two examples will involve wetting, complete wetting by a nematic phase of a hard wall isotropic interface as you approach the bulk isotropic nematic transition. So we're in the isotropic phase, but we're changing the bulk concentration towards where the bulk phase transition occurs. So you've got a hard wall, purely hard wall. These rods interact in a hard fashion with the wall. This is the bulk isotropic, that's the nematic phase, and the results I'll show you are for a ratio L over D equals 15. And the simulation results for the coexisting densities, these again are dimensionless quantities, are these numbers here. Now C is defined in this fashion. Rho is the number density. These are results from an old paper now from Marilyn Dijkstra, René van Rooij, and myself. And so in this case, we're about 8% away from the bulk isotropic nematic transition. Look at this picture first. So the bulk isotropic phase is over this side. Here is the hard wall, and you see you getting nematic-like ordering with a certain width at this concentration. This is looking down. This is looking from the top, or if you like, looking this way at that. And you can see the nematic order there as well. If you get closer to the transition, so this is about 4% away, you see you're growing a thicker film of nematic-like behavior here. This again is still the bulk. And you can see it's strongly nematic at the wall. And then this was about the closest we could go. No, actually, we went closer than this. This is the best picture I've got, where you see a very thick film of nematic-like ordering. And by analyzing order parameters associated with this, we actually showed there was a very strong indication of complete wetting by the nematic phase. And in fact, the thickness of that film diverges logarithmically as you approach coexistence, as it should from the general theory of wetting phase transitions with short-range interactions. Now, a picture which maybe illustrates better what I want to talk about, or an example that illustrates better, is a paper published about the same time by Mike Allen, and this is for hard ellipsoids. And this is both computer simulation and using the second virial Onsager functional. I'll explain that in more detail as we go along. So again, Mike has nice pictures here, nematic-like, liquid-like, an interface between them. He has a wall here which orders the nematic phase at different angles. These results here involve order parameters for the system. So these are order parameter profiles as a function of distance from the wall. So the interface is somewhere in the middle. One set of curves are simulation results. The others are the results of Mike's calculation using the Onsager functional. And you can see that for this sort of size ratio, 15, it does rather well. This very simple second virial functional captures most of this physics. Some would say all of this physics. So, what have we learned? Well, the Onsager functional and some of the early density functional theories which built upon this work well for many of the properties of inhomogeneous fluids, in particular when you have a large aspect ratio. And as expected, Onsager performs well in that regime. However, it is known from the work of many people that when you go to, say, short spherocylinders or other shapes, Onsager does not do well. So I now want to switch tack and say, can we now learn from another piece of theoretical physics, which is density functional theory, classical density functional theory, which was developed primarily for simple fluids, atomic-like fluids, which are essentially spherical. So switching to the other limit, if you like, and then we'll come back to the Onsager limit. So here is going to be a whistle-stop tour of what DFT is, what it does for you, what it doesn't do for you. So the aim of the theory is to calculate thermodynamic properties and structure, meaning one-body information like I've showed you, density profiles, but also pair distribution functions, etc. And you're doing this for inhomogeneous fluids. If you can do this, you can discuss phase behavior, different types of phase transitions. It's a technique that complements both Monte Carlo and molecular dynamics, and it's applicable these days to a wide variety of model fluids. It does start from a proper microscopic base. So there is an underlying Hamiltonian that describes the interactions between the particles. So it fits naturally. I won't go through this. This is a year one statistical physics slide for you. Like molecular dynamics and Monte Carlo, it attempts to go from an effective Hamiltonian through the machinery of statistical physics, calculate observables, relate to experiment, find that you've screwed up, go right back and improve the Hamiltonian. We all know that. At least I hope you all know that. So what's the basic idea? The basic idea is one focuses on the average density in the system, the average one-body density. So these triangular brackets represent an ensemble average, a Gibbs ensemble, let's say, and usually I'll be doing it grand canonically. So minimizing the grand potential functional will give me the equilibrium one-body density in the system. And the corresponding free energy will give me the equilibrium grand potential. So always recall there will be a chemical potential in this system. Moreover, if I take further functional derivatives with respect to the density, I will get the correlation functions in the system through the venerable Ornstein-Zerniger route. And I will show you that quickly. What are the advantages? Why do all of this? This is a technical thing. I mean, very often you can describe or even calculate some rules which relate thermodynamics to structure. And you can do this in the framework of functional differentiation much more easily than you can do by working with a partition function directly. Of course, they have to be equivalent. The other key idea is that for a given model fluid where you have some interparticle potential, let's call it phi, it needn't be pairwise additive, you can find approximations for this intrinsic free energy functional that I'll come on to that should be applicable to all types of inhomogeneities, whether we're doing ordering it in interface, whether we're doing a liquid-gas interface, or whatever, in a gravitational field, the same functional should be true for a given model fluid. So what you show is that this this object, this free energy, is a unique functional of the one-body density. Its form doesn't depend upon whatever external potential, whatever wall or gravitational field you have in the system. A big disadvantage, and I've been guilty of this on several occasions, one might think you have an intelligent model functional, do lots of fancy physics with it, and then find out it doesn't actually correspond to any real physical system. In other words, there isn't a Hamiltonian that corresponds to the functional. And then you can be in deep shit. Yep. Well, it's still fun anyway. Here are some recent reviews for those of you who don't know about the subject. I recommend the first to you. The last section of this review has a section on simple models of liquid crystals. In other words, models for lyotropic crystals. This is a kind of gentle introduction, this one by Roth. And there's a comprehensive review, but it hasn't got things on liquid crystals. It does talk about dynamical DFT by Lutzko. And again, if you want some sort of pedestrian introduction to the subject, there are two sets of lecture notes which I've written down here. These complement each other. The one by Leuven does talk about freezing liquid crystals and dynamical DFT. So the formalism. There's the Hamiltonian for n particles, classical kinetic energy, interaction between the particles, and then the interaction with some external potential. As I say, it could be a wall, it could be a gravitational field, it could be whatever. Not necessarily pairwise additive. The grand potential is minus kT, the log of the partition function. Obviously, it's a function of temperature, volume, chemical potential, mu, and it's a functional of the external potential. Ordinary statistical mechanics says that if you want to get the average density, right, this is the average of the one-body density, it's a density operator if you like, that's just the derivative of minus omega with respect to u, where u is mu minus v external. So this is essentially d omega by dv external, and I hope you all know that result. So the way you calculate correlation functions in ordinary statistical mechanics is you take a second derivative. So this is the density-density correlation function, whose Fourier transform, for example, you would measure in a scattering experiment, at least in a bulk system. That is nothing more than d rho r1 by du r2. So if you go to a bulk system of constant density, a uniform system, this object g of r12 by translational invariance only depends upon the distance between particles. This is related simply to the radial distribution function that you learn about when you study theories of liquids and you do experiments on liquids. DFT takes a different track, a complementary track. It focuses on functionals of the one-body density rho of r, rather than on the external potential u. And so you can prove, and the proof goes back to the work of Hohenberg, Kohn, and Mermin on the interacting electron gas. In fact, many of these ideas were borrowed from the theory of electronic structure. You consider a probability distribution, the usual one in the grand canonical ensemble. Remember, this is the partition function. You show that this is uniquely determined by the density, and so this object, which is called the intrinsic free energy functional, why? Because this is kinetic energy plus potential, so this is internal energy, and this is minus Ts. Remember, the log of F is an entropy, so this is a U minus Ts, so that is a Helmholtz free energy. You find that this is uniquely determined by that. It's also a functional of the density, and then you just keep going, and you derive this basic variational principle. So make a Legendre transformation. Remember, this is mu minus the external potential. This object is a grand potential. When you minimize it with respect to rho tilde, it obeys this minimum principle, and it gives you the equilibrium grand potential. So the equilibrium one-body density minimizes the grand potential. And that allows you to create an alternative hierarchy. You simply now take functional derivatives of what's called the excess piece of this unique free energy functional. So you take off the trivial ideal gas piece, right? The rho log rho term you take away. You define this as the excess. That's to do with all the interactions between the particles. And you set up this hierarchy. And those are called the direct correlation functions. They carry the name C. So you have C1 for one, C2 for two derivatives, etc. And an intuitive way of understanding this is that the Euler-Lagrange equation that you get by minimizing it looks like this. So you fix the chemical potential in an inhomogeneous system that is constant through all of space. And so this expresses its constancy. That's an ideal gas term. That's the external term. And this is the interaction term. So this acts like an additional one-body external potential. But of course, it depends self-consistently on the density you're trying to get by solving that equation. You can write it like this, and then you see why it's an exponential, because you're doing Boltzmann statistics. If I turn off the interaction between particles, I have an ideal gas in, say, a gravitational field. You'll see this is nothing more than the barometric law. This is mu minus the external potential. That's gone to zero. So I'm just getting back the barometric law. If you take another derivative, and you remember what I showed you earlier, you find that this second derivative has a term which is just the inverse of the density-density correlation function. So if you look at the definition of the inverse, you find that C2 and G are related by the Ornstein-Zerniger equation from 1914. These guys working in a cellar in Groningen in the Netherlands worked all of this out. Remember, they did the theory of critical opalescence. Well, they didn't do it this way, but they worked all the idea out of how the direct correlation function can be used to understand critical opalescence, the scattering of light near the critical point. Of course, this isn't to everyone's taste. This has been my experience on several occasions, especially with the help of fluid interfaces. They just fall asleep. Yeah. Of course, one needs to find appropriate functionals for the particular problem you're looking at. So now let's switch to approximations. The only case we know exactly are hard rods in one dimension, from the work of Perkins and the work of Carmen Varela and Alberto Robledo in the 70s and 80s. So you know the functional exactly for hard rods in one dimension, right? That's equivalent to knowing the partition function exactly, which you do know. For everything else, you have to use your intuition. So it's physics rather than mathematics, right? Finding systematic approaches is not easy. They do exist, and often they get you nowhere. Usually they are mean field in character. What does that mean? It means if you look near a bulk critical point, you don't capture all of the aspects of bulk fluctuations. You would get mean field exponents. Now that can be put right. There are ways of correcting DFT to give you the correct bulk exponents. If you look near an interface, they don't capture all the effects of capillary wave fluctuations, the thermal fluctuations in the interface. As far as I know, no one knows how to put that right in this description. So it's been successful when you have strong first-order transitions. It's a very good description for first-order phase transitions at interfaces and in adsorption problems. It's also widely used nowadays to study the bulk freezing transition. This is emphasizing what I've said already. You use, unlike the electron case from where it comes, where you have only the Coulomb interaction, you really are striving for a single unique functional. Here you have to use some intuition. So now let's move to hard spheres, the simplest possible case. Hard sphere potential, you all know. So it's an infinite potential called it D for R greater than D. This is perhaps the most studied system of all, and I'm reminding you of the phase diagram. It's the simplest phase diagram in nature. This axis here is the volume fraction, phi. So it's the fraction of the volume occupied by the hard spheres. Close packing is somewhere over here. Forget the glass for this talk. What you have is a fluid phase which runs up to this value of the density or volume. Then you have fluid-solid coexistence, and then you have the FCC crystal. And there I've just defined the volume for you. So the first thing you would like a theory to do is to give you this phase diagram, right? Starting from essentially first principles. Now there are a plethora of approximations for the free energy functional for hard spheres, and indeed for hard sphere mixtures. So if you have more than one species, I labels the species, let's say it goes from 1 to nu, then you have dependence on the densities rho I. Perhaps the most successful of these came in 1989 with the work of Rosenfeld. And I'll talk a little bit about this. One of the interesting things it does is that when you take two functional derivatives of this to get the direct correlation function, you end up with precisely the Perkins-Yevik direct correlation functions, which are rather accurate for hard sphere mixtures, and were obtained from totally different route by Perkins and Yevik, worked out by Lebowitz. So that's one observation. The other reason for talking about this is that this lends itself to non-spherical bodies. There is Rosenfeld, a close friend of mine. He was a sort of mystic in the statistical physics of liquids. He had an incredible intuition, I would say, a lot of it geometrically based. Here quickly is what it does, and then I'll give you some details. So what you're trying to do is to write down an expression for this excess free energy density. We know the ideal gas piece, which I've taken off there. I'm just writing that out again for you, and this is for a mixture. So I is the number of components and of species rather, goes from 1 to nu. And his idea was to write this as an integral over all space of a function. Phi is now a function of these new densities, which are called weighted densities, n alpha. Alpha is a weight index that I'll come to. And the sort of physics in this is that you have the actual densities, which of course can be as oscillating. If you have a fluid near a wall or in a crystal, those one-body densities will be oscillating. They'll have much structure. The idea is you multiply these by some smoothing or weight functions characterized by some index. I, again, is the species. And the object you get here is much smoother. And you put those much smoother things into a function. Of course, you have to find this function. You've got to argue, does it exist, etc. Geometry will help determine what these weight functions are, and we'll come to that. Note that these are linear in the one-body density. Just an example of how this does, first of all. Right, so this is a hard wall, and then I bring hard spheres, and this is at rather a high density. This is 0. In these units, that's the same as volume fracture. That's 0.43. It's getting fairly close to the freezing density. So there's a lot of structure. The symbols are Monte Carlo simulations, and the lines are the results of two variations of this Rosenfeld treatment. I'll mention this one later. And you see it does a rather good job of it. If you look at the wall, this is a blow-up region. Even close to the wall, the theory does well. It captures essentially all the structure. How did Rosenfeld get this? And this brings us, in fact, to the Onsager functional. The starting point is, to a large extent, like that of Mr. Onsager, though Rosenfeld is doing spheres. Yep. So it is known from the virial expansion, from the diagrammatic expansion, that as all the species densities go to 0, this excess free energy is just an integral over all space, right? So I haven't got any orientation at the moment. I've got just spheres. the product of the densities times the Meyer function, which I've called Fij. So that's the Meyer function. It's e to the minus beta, the pair potential. And in this case, we have just hard spheres. We have hard spheres of different diameters, different Dij's sitting there. And so for hard spheres, this works out. It's just minus a Heaviside function of this difference. More generally, of course, you can write the Meyer function between bodies I and j located at positions rj, ri as 0 if the intersection of the two bodies is 0, or the overlap, rather, of those bodies is 0, and it's equal to -1 if they don't. So remember that. We'll come back to that. We'll use that when they're non-spherical. Okay? So in this case, this is a very simple object. So this is a rather simple quantity. So Rosenfeld's idea was to rewrite that equation for this set of pair functions in terms of these weighted densities. And these are the building blocks of the theory. And what he found is he can do this, and this is not a unique decomposition. Other people found other ways of doing it, but this is in many ways the most powerful. What he found is he could write that Meyer function in terms of convolutions, right? So the 3 terms here, and then there are actually 6 because you swap the indices I and j. And these weights, as they called, are simple geometric functions. Again, this is a Heaviside function. That's a Dirac delta function. And this one here, again, has a Dirac delta. So they're functions which are defined either through the volume of the sphere or on the surface of the sphere. They're very simple. And the others are written down here. They're related to those. So there are 6 weights. And that is enough to deconvolute the Meyer function. And the convolution product I've just written down here for you. This is shorthand for performing that integration. So for any hard spheres, I should say any additive hard spheres, this is an exact deconvolution. And you have, in this case, 4 scalar functions, 4 scalar weights, and 2 vectors. So I've skipped here, or I'm skipping here a scalar product if these are 2 vector functions. So in the low density limit, if you just go through the algebra, you see this functional, Onsager functional, low density functional, is very simple. It's just a sum of 3 terms which involve these weighted densities. Once again, that's what they look like. And this motivated then Rosenfeld to say, well, what happens for non-zero densities, at arbitrary densities? Can we write something very similar? And then comes intuition tricks. First of all, he used an exact result from scale particle theory, mixed with a bit of dimensional analysis. It's a magician's box. And he found this. So he found, well, this is the postulate, that for arbitrary densities, you can write it in terms of an integral over this function, and this function just depends upon these weights through this. So these are the weighted densities, these n. So this is a sort of guess at how you go from low densities to high densities. And that was what was used in the calculations I showed you. So for those who know a little bit about it, this reduces to what's called scale particle theory for the free energy density of the uniform fluid, and as I said earlier, to Perkusiewicz for correlation functions. Those W's only depend upon the geometry of the particles. That's where the term fundamental measures, it means fundamental geometrical measures, come from. Many people attempted to improve upon this with some success, in particular Tarazona. Tarazona had again great insight, and he introduced not just vector weight functions, but tensor weight functions to take into account some of the more subtle aspects of the geometry. And that was motivated by earlier work of Tarazona and myself, which looked at what's called the 0D limit. That is a limit where you confine a hard sphere very strongly in a cavity which can only hold one particle. In that limit, you know the free energy exactly. So you can require this theory to reproduce the free energy in 0 dimensions, this extreme confinement. And there are also empirical improvements. One which is perhaps the most accurate we have is called the White-Webb version. I won't explain this to you. I'll just show you the research institute where the theory was developed. How well does it do for freezing? Sorry about the numbers. These are very recent calculations by Martin Oertel in Mainz. And these are densities. Forget this and forget this. Just look at the theory here. This is the White-Bear version 2, and these are the simulations. So these are the coexisting densities for hard sphere freezing. Compare those two numbers with these here. They do very well. This is the value of the free energy at coexistence in each phase. Again, it does rather well. The chemical potential is accounted for. And very interestingly, you have vacancies in these systems. So the FMT that's used here takes into account that you have vacancies, as of course does the simulation. That is a difficult thing to do, and the theory gets a reasonable concentration of vacancies compared with the simulation, better than anything else. These people looked at the surface tension between the coexisting crystal and the fluid, and on different faces of that crystal. And again, the surface tensions do rather well compared with simulation. So the more sophisticated versions are rather good. So now let's get back to the actual problem. Now we've got shape. So we're coming back, if you like, to Onsaga's situation. We're going to look at spherocylinders in particular. So Rosenfeld in 1994 tried to generalize his work to something that's got shape like a spherocylinder. And so he considered a point on this object here. That's the surface normal. This is just the center of the body, and that's a unit vector r going to that point there. What he did is he looked at the mean curvature, let's call that h, and the Gaussian curvature ki at this point. And he asked, could he build that in to his FMT functional? Again, it was very intuitive. And this is what he did. He changed those weight functions. So these are the same objects that we talked about before. There are 6 of them. I'll just go through this quickly again. You should read the paper if you want to understand it. But what's now appearing, you see, is the mean and Gaussian curvature sitting in front of this. So he recognized that the coefficients that were in there for spheres should be generalized using curvatures. That's basically what he did. There again is the definition of the mean curvature, and that's the Gaussian curvature. So obviously in spheres, these reduce to very simple things like 1 over r. And then he generalized the weight. Sorry, he generalized the weights. We've done that already, the W's. And so the weighted densities now involve integration over orientation as well as position. And following Onsager, he's treating orientation as just an infinite number of species. So what I've actually written down there, if I keep the I here, this means I could have different species of hard particles. I could have big and small, etc. So if you like, if it's easier for you, take away that sum over I. It looks appealing, but it's not quite right. What does it do? Well, for a uniform isotropic fluid, for particles of any shape, as Don sort of pointed out, that's an easy calculation to do. It's the case where the warm body density is just a constant. You can show that the Rosenfeld formulation gives the exact second virial coefficient. So this decomposition of the Meyer function is exact in this case, using those weights. Yeah? But when you go to anisotropic phases, again, it's rather straightforward to show if you have just the one body density being the density times the orientational distribution function, you can show it's not exact. Right? The free energy, in fact, is independent of the orientational distribution function. So you haven't got that right. So it's not surprising that it doesn't yield an isotropic nematic transition. So it looks elegant, but doesn't give the transition, so it's really a non-starter for doing phase transition problems. I'll explain why it, in more detail, why it goes wrong when we come on to the more recent work. So I'd recommend, the paper I'm going to talk about is the second of this in Journal of Coordinates Matter. Never read phys rev letters, they never tell you anything. Well, Nature and Science are worse, they tell you even less. Read a good journal, a good British journal. Yeah? So what does it do for you? Actually, seriously, it's a beautiful paper. I spent some of the last 10 days trying to get to grips with this. It remedies Rosenfeld. It captures the transition for rods, for cylinders in other words, and it does this by focusing properly on the deconvolution of the Meyer function back to Onsager. Yeah? It introduces a series of tensorial weight functions, each depending upon the shape of a single particle. And it does it in a different way from earlier work of Friedrich Schmidt. I'll have to go through this quickly. I can see we're running out of time. So this is the result we saw before. This is equal, the Meyer function is equal to 0 if the intersection is non-zero, otherwise it's equal to -1. And like Rosenfeld, these people go back to the Gauss-Bonnet theorem. So here is the Gauss-Bonnet theorem written down for a single body. This now is the geodesic curvature. And here's my poor attempt at trying to draw this. This is a single body with shape. This just takes me to the center. This is the body BI. Let's make a curve on the surface of that body. We've got a unit normal, and this is the principal normal to the curve. That's an angle lambda I, so the geodesic curvature is just given by that. Kappa is the circular curvature. So that's all standard. So what the researchers did was now to look at the intersection of two bodies. Right? And I've drawn them with different shapes just to show that this is quite general. So I'm looking at the intersection, and I look at this part of the surface, the red part, and the green part. And then there is a single bounding curve, which I call C. So two surfaces, red and green, bounded by a closed curve. And apply Gauss-Bonnet to that. And it gets complicated. The starting equation looks simple, which it is. So this is just a simple rewriting of Gauss-Bonnet for this geometry. And of course, from this, I can go straight to the Meyer function. So the Meyer function, writing it out, for arbitrary convex bodies can be written like this. This is Gauss-Bonnet, right? And then what these people did, this is Mecker, what they did was to focus on this term here. So you keep those two terms there, and remember they're extras because I can have I replaced by G, and I rewrite this integral over the geodesic curvature. And that's where all the hard work comes. It gives this term, and it gives this, where this is a difference between curvatures. That vanishes when you have spheres, and all of this spells it out. So that term here, which vanishes when you have spheres, this difference, the deviation vanishes, they now keep. They do the geometry properly and rewrite that in terms of these weight functions and therefore the densities. So you end up, and I'm just about done, you end up with expressions that look like this. These are easy. You can write these as convolutions. The one that you can't write as a simple convolution is this. So all of this is still exact if you keep this. These are just vectors, these v's. These are unit normal. So the problem is you can't write this as a polynomial anymore. So you can't write it in this simple form because of this denominator. So what you have to do is to expand it. Remember, these are unit normals. That's dotted into that unit normal. So then you have to make approximations. And that's where the new research comes. How do you make approximations for that? And that's what they do. One thing is to simply write that as a constant and find a way of estimating what that constant is. And the way you do that is you work out the excluded volume in the non-isotropic phase. And that's a way of almost self-consistently determining what that is. So what you end up with, if you do that, is just this extra term here, which depends on a constant to be determined, the ways of doing that. And here are the first set of results, right? This is the volume fraction versus d over L, right? So the Onsager limit is here near 0. This is a blow-up of this region. And you see this does reasonably well. You can't see the difference in coexisting densities when you get in this region, but when you down here, depending upon how you choose this zeta, this constant, you're reproducing the coexisting densities reasonably well. Later developments which are not published, where they don't make this approximation, they include tensors of higher rank, do even better than that. These are density profiles of an isotropic phase away from wetting at a hard wall. I won't go through all of it, but again, the theory does remarkably well in accounting for the details of the one-body density profiles in this very inhomogeneous system. And so there's a summary of what they're currently doing. Wittmann is a student. They're including higher rank tensors. In other words, to get the 1 over 1 plus ni and j better, they're working with higher order constants, higher order ranks rather. They've investigated the interface and do rather well compared with simulation. So this is surface tension in this case. They can calculate the Frank elastic constants by calculating the direct correlation functions. They take 2 functional derivatives, right, of the free energy to get C, that gives the, and so forth. Turns out this is intimately related to stuff that goes on in 2-dimensional disks. You have to work hard to do the deconvolution of the Meyer function there as well. So conclusions, it is of course difficult to improve upon Mr. Onsager. We knew that when we started. There is recent progress. I think it's an area where applied mathematicians should be able to contribute. I think there are tricks in differential geometry which I don't know about, which could be used for these problems. There are of course many other topics which I haven't had time to discuss, so I apologize for going on too long. Thank you.
Yes. Right. So we still have time for a couple of questions at least, because we started with a few minutes late, so please. So maybe I can start by asking, is there some simple, although maybe idealized shape by which you could get a simple or relatively simple expression? Or in other words, is ferrocylinder the best or ellipsoid?
Good question.
Or can you find something?
I think it's a good question, Claudia. Yeah, I mean, I think the background here is that people are obsessed with Onsager for good reasons, right? So ferrocylinders are always in the back of your mind. But once you move away from that limit, I think there is no good reason. So, you know, whether it works better, I think what you may be asking me, does it work better if you go for other shapes? No one's tried it yet. I think people will continue with ferrocylinders in the first instance. Yeah. Mike.
Here's a pesky question that I've asked you before, and I've probably just never understood the answer.
And I will have forgotten.
Yeah, well, hopefully, yeah. So, as you reminded us right at the beginning, in the Onsager limit, there's a well-defined isotropic pneumatic surface, an interface, with a well-defined width, which doesn't do anything pathological. It's you know, of the order of a fraction of the length of the rod when you rescale things. And as we've heard, Onsager should in principle be exact in that limit, and yet at the same time, as you said, it does not include the capillary wave fluctuations. So I'm worried now. Is there a paradox there?
I think
are they in there or not?
I think it's a bit like, is Don still here?
I had to go after a meeting.
It may be in some sense a singular limit for the interfacial problem. I think it's a very special case. So the short answer is I don't know. But I do think it is of the nature of a singular limit when you do this. I mean, you do get a surface tension of sorts. So that there is a stiff interface, and so you could say that there should be capillary waves on top of that. But then, if that's the case, the functional hasn't put them in. That's what we're discussing. Yeah.
Speaking of shapes, is there any attempt to extend this machinery to non-convex bodies?
Not by me, no. As far as I know, not by others. I mean, as you can see, it probably all breaks down. When you start to do Gauss-Bonnet type things for non-convex, it's messy. So if you're asking, can you deconvolute Maya functions when they're not, well, you're very welcome to have a go.
Thank you.
Ask another quick question. I mean, one result from experiment and also from simulation that we also have done is that if you have a wall which has some direction, some order, for example, the face of the crystal, then the local order is increased, and vice versa. If it is a degenerate wall, it is decreased. Is this simple result obtained by this kind of?
It should be. I think all of these, as I started at the beginning, I mean, the motivation for doing this is to have something that's sufficiently accurate that captures all of the sort of phenomenology that one might expect. I don't see any reason why not.
But this would be.
Yeah. I mean, you're guaranteed, for example, that you get wetting behavior, and you're going to get the right behavior too. Right. And if there's any local biaxiality, for example, there's no reason this shouldn't be encompassed here.
If you had a rectangular rod and you approximated it by smooth volumes, do you know whether these approximations would be well behaved based on curvature?
That's a good point as well. I mean, obviously, one is starting by drawing things that occur, because that's the sort of physical picture. But no, I think no one has looked at this. I should say that it's a kind of small community that works on these problems. But Friederike has put her hand up.
We have Friederike and Mark, and then maybe we stop.
It's about this Mecke-Gauss functional. Does it get the Onsager limit right? Or do you
which one, Friederike?
The Onsager limit, like the L over D to infinity limit, does it get that right?
You mean the Mecke?
Yeah, or do you need infinitely many terms for that?
I think, again, it's not public, though, as you know. I heard the talk by Mecke 2 weeks ago. I think, and we,
Yeah, I missed that one.
And I think the implication is, and I may be getting it wrong, the implication is you need the infinite. So you need a set of infinite rank tensors. Now, whether you can resum something and account for it, God only knows, I think. I don't think they want to go that way. Yeah.
I have a similar question. If you go back two slides, perhaps.
From the end, Mark.
Yes, yes, from the end. No, yeah, that one. How does that actually compare with experiment?
Down in this limit, you mean, Mark?
No, in the other limit.
On the other limit where
the shots are shorter.
I mean, Mike, I guess, can answer better than I can, given Don's not here. I mean, I think it's not bad up there, isn't it, Mike? D over L about 0.25?
Well, I can't remember.
Well, for lyotropic systems, well, of course.
Yes, that's what I was concerned about, because this was one of the great holy grail.
For rods, yeah.
Florey, trying to calculate what the athermal limit actually was, and he came up with a number 6.4. I.e., if they were longer than 6.4 at finite densities, it would always be pneumatic. And I just wondered how that fitted into this general scheme.
Well, I mean, here, you see the computer simulations here. They keep going even further if we were to go out this way. Yeah.
Right.
I mean, the distinction, as you can see those dots, that means there's there's essentially no density difference between the two coexisting phases. That's what happens as you go that way.
Right.
But there's a transition mark.
Yeah, absolutely. But Florey was saying the opposite. When you go that way, there comes a point where there's no more isotropic phase at high densities. And I guess that's what that diagram is saying.
Well, it hasn't stopped yet, though.
Yeah.
Yeah.
Well,
Yeah.
Okay. So we can thank